Hi everyone. We're going to start off the course by doing some review of pre-calculus. In particular, we're going to be reviewing exponential functions, which is section 1.4 of your textbook, and logarithmic functions and inverse functions, which corresponds to 1.5. So let's start off with exponential functions. We all know what they are, I hope. A function of the form f of x equals b to the x, where b is a constant bigger than 0, not equal to 1, is called an exponential function with base b. And what do the graphs of these exponential functions look like? There are actually two different families of shapes. There are ones that go up as you go from left to right, and then there are the ones that go down as you go from left to right. So what decides the shapes? And the answer is the value of the base. If you notice, all of the ones that are increasing as you go from left to right have a base that's bigger than 1. Let me just write that down. And the ones that are decreasing as you go from left to right are ones with the base less than 1. But of course, bigger than 0, because it's an exponential function, by definition, b is assumed to be bigger than 0. And for all of these cases, there's a horizontal asymptote at the x-axis. Remember what horizontal asymptotes are? They're the lines that the graph gets closer and closer to, whether you go towards the right forever or you go to the left forever. We'll talk a lot more about horizontal asymptotes in chapter 2. Alright, so let's look at some properties of exponential functions. Notice that no matter which graph you're looking at here, they all go through this point. That point is 0, 1. And the reason why they all go through that point is because they all have this formula. If I plug in 0 for x, I get y is b to the 0. B to the 0 is 1. So the reason why it goes through 0, 1 is because b to the 0 is 1. Now let's look at the domain. The domain of a function means all the x values that you can have so that the output is a real number. Now, x can be any real number you want. Because b to the any real number exists, that means the y value exists. So the domain is all real numbers. You can plug in any real number you want into x, and you get a real number as y. Now let's look at the range of your function. The easiest way to figure out a range is by looking at the graph of your function. So let's go back up here and look at what kind of y values they take on. No matter which specific graph you're looking at, every one of these graphs will get closer and closer to this line without ever touching it. So the smallest y value is some number really close to 0, but a little bit bigger than 0. And the largest y value, well, there isn't one because all of these just go up forever. So in conclusion, the range is all real numbers starting from 0 all the way up to infinity. Let's write that in interval notation. It would look something like this. Open bracket, 0, to indicate that 0 is not included, right? And all the way up to infinity, again open bracket, because infinity is not a number. It's not in the range. And as we mentioned earlier, there is a horizontal asymptote here at the x-axis. The equation of the x-axis is y is equal to 0. Now, of all the exponential functions, there is one base that is going to be used the most often, and that base is the number e. Now, e is an irrational number, meaning it can't be written as a fraction of two integers, and the first few digits go like this. You should at least know the first 3 digits of e, so e is approximately 2.71, or 2.72 if you'd like. So if we set that as the base of our exponential function, then of course we're going to get y is equal to e to the x. and that has a name. It's called the natural exponential function. Now, one thing I didn't discuss when we looked at all the different graphs of exponential functions is, for example, when we look at these ones, the ones that are increasing because the value of b is bigger than 1, why do they all look slightly different? Well, it turns out that if you look at the base, the bigger the value of base, the steeper your curve is to the right side of the y-axis. So notice that this is not very steep because 1.5 is not a very big number. But as we go bigger and bigger, you're getting steeper and steeper on this side. So hopefully you can see what the graph of e to the x will look like. Well, it'll be somewhere between 2 to the x and 3 to the x because e is between 2 and 3. And it turns out that it's actually this pink curve here. It's closer to 3 to the x because e is around 2.7. It's closer to 3 than it is to 2. Next, we're going to look at some laws of exponents. All right, so let's figure out a different way to write a to the negative x. In particular, I want to write this without the negative exponent. And hopefully you can all remember doing this in high school. You can write it instead as 1 over a to the x. For the second one, we have a to the x times a to the y. If I want to write it as a single power of a, we can add the exponents. So this is the same as a to the x plus y. Similarly, if I want to write this using a single a, what we can do is subtract the exponents. So this is the same as a to the x minus y. For this one, if I wanted to write it as a single power instead of one power and then another power out here, you can multiply. So a to the x to the y is the same as a to the xy. For this one, we have two different things multiplied, all to the power of x. Well, it turns out you can distribute the x. So a times b all to the power of x is the same as a to the x times b to the x. And finally, similar idea here, you have a over b all to the power of x. Well, that x applies to a and b, so it's a to the x over b to the x. Now, knowing these laws of exponents, you should be able to do the following example. What I suggest is that you pause this video here and work on it yourself, and then when you're done, restart the video. But I'm going to go right ahead here. What we're going to do is make the bases on the left and the right the same. There is a base 3 on the left side, and there is a base of 9 on the denominator of the right side. If you can write both sides with the same base, what you can do then is equate the exponents. Right, if the bases are the same, then the exponents have to be the same as well. So notice that this is already simple on the left side. So what we will do is we take the right side and let's write it with base 3. So 1 over 9 to the x is equal to, well, first of all, I don't want this 1 over. I just want 3 to the power of something. So what I will do is look at the laws of exponents again, in particular this one here. So we have something like this. So let's go backwards. Let's write this as 9 to the negative x. So this looks better. We got rid of the fraction, but it's still not base 3. Well, 9 is 3 squared. So let's rewrite 9 as 3 squared. And let's simplify this a little bit. We have a situation like this here where you have two different powers. We can multiply them out. So we get 3 to the negative 2x. And now we have a power of 3. This goes here. And what we're going to get then is 3 to the x minus x squared is 3 to the minus 2x. Again, since the bases are the same, the powers must be the same. So let's just equate the powers. So x minus x squared is minus 2x. let's bring everything onto the right side. So you get 0 is x squared minus x minus 2x, which is x squared minus 3x. And that means 0 is, let's factor out the x, so we get x times x minus 3. So there are two different values of x, 0 and 3. It's easy to verify that your answers are correct by plugging in each answer into here, making sure that the left side and the right side are equal. So hopefully all these topics are coming back to you from when you learned in high school. And I'd like you to do some homework. So all these questions come from the textbook. Not too many here. And once you're done with those, we can move on to the next section.